Hello. Yeah, I just had to make sure to test some stuff. Also, the balancing on this is kind of... Let me turn that down. I think I should be louder. Just in case, I'm gonna go to my own stream. I think I should be louder. Just in case, I'm gonna go to my own stream. Okay, yeah, that works. All right. So, then I gotta open my notes. So I made notes. Oh shit. Okay. So when we actually start, I'm going to stop the music because I literally do just want to focus on like doing lecture related things. Oh shit. Fuck. Damn it. I dropped my little pen thing. There we go. I wanted to do study streams, but I didn't really want to chance it on the textbook copyright, you know? Like I'd have to look into it. I could send out some emails and see. Because some of them are from lecture notes and stuff. So that could be fun. Either way. But I have prepared, like, actual lecture notes this time. 12 whole pages. And so once the clock hits 7:30... Oh, I should actually also, real quick, just, like, advertise my own stream to my friends. Because I'm a nerd like that. Also, I gotta real quick mute the tab before... No, okay, good. No one else's stream audio played. Ha. Ha ha ha. Alright. And I just hit this. And then I can just hit the, Alright. And then I'm gonna send this to a few more people so they can, like, throw it on the background, or if they would actually be interested or whatever. I'm also gonna send it to my friends who I was just in a call with, a little bit ago, because I do wanna see who is actually interested in the subject, you know? Like, even among my own friends, I do want to get more people into it. So yeah. We're about 1 minute till we start. Oh, and I do have to have a... Hold on. I do also have to have a good split for my stuff. So this can go on the right side of my screen. And then this can go on the other. So that way I can scroll it. Nice. Yeah, I will be uploading those notes. I'll be uploading those notes on like Dropbox or something. I don't know. I'll make sure I add it to my YouTube. I don't know if I'm gonna put it in my bio. It'll be available in my Discord as well. So hopefully I updated the link properly for that. Anyway. Alright, it is the appointed time and hour. Oh, wait, hold on. Oh. I sent it to my another one of my friends by accident. There we go. And then I suppose you. Oh, and I guess why not? Actually, you're asleep. All right. Oh, hello! Oh my God, you're in time. Okay, hold on. I gotta stop the music. So, and let me go to my There we go. There we are. We're much more locked in now. So, we're going to be starting. Oh wait, do I? Okay, the chat works. We're going to be starting with I guess fundamentals of calculus, right? So, in my lecture notes, I go over sort of why I'm like doing this series a bit more, and I also haven't really practiced the speaking portion of this because I finished writing it just today. So if I'm a little stuttery, that's why. I'm not well practiced on it. But if you're watching this series, you're probably someone who's either interested in me as a content creator or someone who's particularly interested in learning physics. So let me give you a little bit of a background on who I am, and why you should and should not listen to me. So as of making this series, this first little episode here, I am in my final year of my undergraduate physics major. My record isn't great, you know, so take everything I say with a slight grain of salt. There's a lot of provided books that I recommend once I post those notes. And the way I structured this is so that you can prepare for the physics subject GRE, basically, right? It's what graduate schools tend to consider the very, very, very basics. And then even beyond that, there's some stuff that you need to know, right? So I'm going to try to focus on a couple of things today. We're going to do calculus from scratch. And then later on, we're going to try to cover classical mechanics, electromagnetism, optics and waves, quantum mechanics. Hold on, let me scroll my lecture notes. Quantum mechanics, thermodynamics, and finally, a little bit of atomic physics, the class I'm currently botching, by the way. This series is both designed to help me review and also be able to teach. If you are in the chat and you are like confused about anything, I do have the chat up on the side alongside my stream to make sure everything is moving smoothly, right? So always feel free to ask questions if you have any. That being said, I'm only assuming knowledge of basic algebra and trigonometry when I teach this, but it might be a little bit faster paced. Also, I am not officially qualified to teach in any capacity, so I'm providing, again, that link to, well, not link, but a list of a bunch of textbooks that you could look up and read so that you don't just have to take me at my word, right? And also, generally, the GRE has more specialized topics that it will talk about sometimes. Though these likely will change by the time I'm done actually delivering all of these lectures. So, that being said, I'm going to skip the discussion of the texts because I have them listed and my thoughts on all of these texts listed. And I'm going to go directly into the fundamentals of calculus. So, we can start from the beginning momentarily. Just gotta get rid of what I have right now. So we can start from the beginning here. But just to let you know, I won't be proving absolutely everything from scratch here. I will mostly be covering things that are either easy to prove or do not require math beyond algebra, right? So we're going to start with a derivative, right? Derivative. Has anyone heard of the concept of a derivative, right? Are you familiar with the concept? I'm gonna give it a second for responses, and if no one responds, I'll just continue. Yes. Okay. Well, could you tell me then? What do you know about derivatives? What is your experience with doing derivatives, taking derivatives? Do you just know the concept? How comfortable are you with this topic? Okay. While you work on that, imagine for a moment that you have some point on this arbitrary little curve that I've drawn. Okay. You're only familiar with it. That's fine. By the end of today, hopefully you have a good grasp on it. So, the basic idea behind a derivative, right, is that you have a point and you can find the slope at that point, right? Little something like that. So, the example that I have listed in the notes, and probably the best example, is a linear equation, right? When we talk about a linear equation, it looks a little something like this, right? Where this is our x-axis and this is our y-axis, right? And we can see this change in y, right? Change in y, and this change in x. So we have our rise over run for the slope. So the way we can express this line in space is y equals mx plus b, where this guy is our slope, right? So that's the very simple part. So then how can you find this for, like, say a curve that looks like this guy here, right? The idea is you can find an infinitely small, like, run and an infinitely small rise, right? Some infinitely small x and y to find the slope at that point. So let's walk through a little bit about how this is done in a more formal sense. Okay? So if we take a more naive approach, right? Say we have some quadratic equation, y equals mx squared. And it should look a little bit like, hold on. It should look a little bit like this guy. How can we find, say, the slope at... I am so silly. There we go. How can we find the slope at this particular point? Well, again, more naively, we can say, well, we know that we want something of the form mx plus b, right? This is our desired form. I'm just going to capitalize it because it makes me more comfortable. Mx plus b. So, if we want something that looks like this that comes from here, we could say that we know two mx squared minus mx squared equals mx squared. So this is a valid expression for mx squared. Next, we can say, what if we have some point P, some desired point, right? Such that P equals x. Now, we can adjust this form to say we have 2mpx minus mp squared. And you'll notice that this slope right here is the value that you will get from a derivative if you take it, right? You can see this graphically if you use a program like Desmos to try this trick, but this method is not foolproof, right? There is a problem with it. So you have to make a guess for higher powers of x, right? So for higher powers of x, this clever guess is x to the n p n minus 1 x minus p to the n. Oh, that's an error in my lecture notes. I gotta fix that. Yeah. Okay, wait. I see an uh-oh. Are we saying uh-oh because we have to make a small guess here for this method? Or are we saying uh-oh because you're not understanding something? Like, where is the uh-oh coming from here? Okay, you can't just say yeah, because the stream has delay. Which one are we talking about? We have to make a guess, yeah. There is a better method for this, where you don't have to make a guess, but that comes from a field of mathematics called analysis. So there is a better, more formal proof of the power rule, right? So it follows. Sorry, I should have given you the terminology first. It follows d dx. This is the symbol for a derivative. Of x to the n equals n minus 1. Or sorry, not n minus. What am I doing? N x to the n minus 1. Right? And this, in turn, is our power rule. Then we have the chain rule. So the chain rule is basically, and okay, so you have some composite function, right? F of g of x. Now, I don't know if you, I mean, I only have one person in chat right now, but do you remember what a composite function is? Like, is that basic algebra? Because I covered that in algebra. I don't know what everyone else's algebra curriculum looked like back in the day, right? Is that roughly where we're at? We know what that is? Maybe? 50-50? Not very. A composite function is essentially a function of a function. So I'll demonstrate this first, but I demonstrate it second in my lecture notes. So say I have some function f of x equals x squared, and some function g of x equals x to the third, right? Then since we have x squared, it's f of g of x squared. So it's actually f of x to the third squared. So then that's x to the sixth. Make sense? Checks out? It's fine if we're a little fuzzy on that. But, okay, good. Then, here's what we have next. So, next we can use the power rule, right? So, from our power rule, we expect, from power rule, dx x to the sixth equals 6x to the fifth, right? That's what we expect. Before I continue, little pop quiz, right? If I were to say I have dx x to the fourth, what is the derivative? Let me know. I just want to know if we're feeling comfortable with the idea of the power rule, just in a very simple sense right now. And while I do that, I'm gonna if we don't know, that's fine. But I would hope that the earlier bit of information is helpful, right? I'll even scroll back for a second. Chew on that one. Chew on that one for a bit. So then we have our chain rule. The way the chain rule is done, right? And I won't be deriving it in lecture because it's a little lengthier and it involves definitions of a limit, which is something that's not covered in algebra. So instead, I'll just state it directly. df dx df dg dg dx. This looks intuitive. The proof is about equally as intuitive. Anyway, so if we use our example from earlier, these guys over here, right? I'm going to box these up for people, right? If we use these guys here, we can try to use the chain rule on these guys. So if we use the chain rule, well, what is df/dg? df/dg is equals 2 g of x. Because we did the power rule with respect to g. And then dg dx equals d dx x to the third equals 3 x squared. So then, going back here, we plug these in. We get 2gx times 3x squared equals 6x to the fifth, which is exactly what we would expect from our power rule. So we've demonstrated that the chain rule will give the same derivative in this case, right? We've shown that the chain rule works. Just remember, I'll write this down, chain rule. df dx excellent. So I didn't have people look over my next section, right? So it's unedited. It might be a little difficult and hard to get through, but we are going to talk about the power rule. Now, this is going to be one of the lengthier sections alongside integration, because the power rule states, essentially, f of x times g of x equals df dx g of x plus df dx f of x. Right? So, I have a very simple proof, right? Sort of revolving around logarithms. Yeah, I'm covering a lot of rules right now. Again, this will be up on the YouTube channel, so you can always look through it. And I will also have a PDF available for people to look through that'll be updated after each lecture. I'm planning on doing one a week, maybe one every 2 if I can't keep up with the workload. But I really do like writing these. Actually, we'll take a beat real quick before we cover the power rule. Any questions? If there are no questions in the next minute, we'll move on. No questions? All right. So basically, I'm going to do a little bit of a derivation here. Say that I have two functions, f of x equals, what these functions are don't matter that much. They matter a little bit, but not really even that much. So, I won't be... You feel like a student right now? Aren't you actually just a student? Like, you're like, still doing, like... I can't remember even what level of schooling you're in, but... Yeah, you're actually just a student. So am I, but... So, I'm introducing something called Euler's number. In the notes, I give these f and x and g and x actual values so that you can choose to evaluate them if you wish. But in reality, they're completely arbitrary, right? So, we have these two functions, right? We have the natural log of these two functions. You should ideally be familiar with logarithms, but just in case you're not, it's basically how many times a number can divide something else, right? So if I have log 10 of 100, that's 2, because this is 10 squared. So, in essence, natural log is it's just log e. It's how many times e goes into something. So ln of e equals 1. Just as a side tangent. So then we can use another neat property of this number that I have given a short explanation for in the notes, where this is an important property of this number, and it's a very nice property of this number. Hooray! So by stating this, we can effectively show, right, And I'm gonna... hold on. Me when I can't draw a fucking square. Bro. Much better. Alright. And this is the product rule. The reason why it's also labeled as the quotient rule is because you can extend this rule to a handier bit of notation that I did not notation, but a handier formula that I did not include in the lecture notes either. I just assume most students will figure that out on their own. Anyway, then you have g of x equals... We all know how exponents work, ideally. Plus so there you go. So you have that. And then when we apply a derivative to this, we can use our handy dandy chain rule that we learned earlier, right? So we can say d dx of this guy up here. We copy you. Of this guy up here equals yeah, okay. d dx of that guy up there. So d dx of this guy up here plus, or not plus, sorry. What am I? Times, oh yeah, there we go. Times just our original values back. F of x, g of x. So, now what we have here. Gotta go for a bit. Alright, fair enough. So, now that we have this set up, right, we can essentially say there are rules that I haven't covered yet because they're a little harder, a little more advanced, but you'll have to take my word for it. d dx ln of x equals 1 over x. So, by applying no, you're good. That's fine. By applying the chain rule again, right, we essentially get the result back of df dx 1 over f of x plus dg dx 1 over g of x times f of, oh shit, not f of g of x, f of x g of x is equal to our product rule. Yay! Okay, so we've spent some time proving the product rule, we've spent some time demonstrating the chain rule, and we spent some time doing a sort of hand-wavy proof of the power rule. These are most of the things you'll need to know when you do a derivative in calculus. However, there is more. Arguably, one of the most important parts of the subject of calculus is the fundamental theorem of calculus. But before we start, I'm going to introduce you to another bit of notation, just so that I don't kill my hands. Ah, shit. I wish I was not a terrible writer. Okay. F prime of x equals df dx. Right? Prime notation. It's great. I enjoy it immensely. People generally interchange between the two depending on which is more convenient. But yeah, the fundamental theorem of calculus essentially states that if you have two antiderivatives, that is the inverse of a derivative, and you take their difference, it is just the difference of the original function, right? But I find that to be a little unintuitive to teach. So instead, I will just show you the notation, and it should hopefully speak for itself. Minus f of a. So, yeah. In essence, we have that the integral, this guy right here, is called an integral. The integral of the derivative of a function over some limits is just equal to the difference between points, I guess, on that function. Right? This is assuming something called continuity. Again, I'm not going to get into that because that doesn't really... Like, if you're a mathematician, you care. If you're a physicist, you always get to assume continuity for the most part until you get to, like, quantum and stuff. You'll understand it better when we get there. And also, note that the derivative of a constant is 0, right? So dx of some constant is 0. So, in essence, this is the fundamental theorem of calculus, but I will give a quick example. If you have some f prime of x equals to just like 2x, right? You can say that this is the same as, we know that by this little fun guy right here, this little bit of intuition, we know that the integral of 2x dx across a and b, or like between a and b, you get it, is b squared minus a squared. Wonderful. Now we have integration methods, and we have trigonometric and miscellaneous identities in calculus. I did not cover identities as related to the logarithm, because derivatives of logarithms are a little trickier, if I'm being honest with you. I actually don't fully grasp the intuition behind how they work myself. I think it's much more obvious with natural logs as opposed to just normal logarithms. But that's because they're nice to work with. Oh, actually, I can derive it on the spot. Basically, this is a little side tangent, but if you're wondering for like the derivative of a log, right? Well, remember that e to the x, the derivative of this, is just e to the x, and you follow the normal chain rule, right? You can derive the rule for any logarithm yourself using this rule, right? So you can say a to the x. Yeah, if you have a to the x and you take its derivative, right, you can just apply the chain rule after you convert a to the n to e to the m, right? This is something you can do. The same is true of converting from log to natural log. You can take the derivative rule for a natural log and get the derivative rule for a logarithm of any type from the definition of a log relative to the natural log. If you have questions about that, you can reach me on my Discord server and I will answer you. 100%. Guarantee it. It's not something I can cover in like a Twitch lecture. Maybe in the video lecture series, I can do that. Not in the Twitch lecture. Absolutely not. Okay. Now we have our integration methods. So, for integration methods, we have something called U substitution. Which basically states that I can do a change of variables, right? If I have x plus c squared, I can say that this x plus c that I have here is just equal to u. So, I bet you're wondering, okay, sure, yeah, you could do that, but why is it useful? Let me show you. I can also write the infinitely small, like an infinitely small change in u relative to an infinitely small change in x. Right? That's pretty cool. That's awesome. So u substitution is then really useful in derivatives, because if I have 1 over x plus c to the n dx, I can simply restate this as, we'll go from a to b here, b plus c, a plus c, 1 over u to the n du, u to the negative n, a plus c, b plus c, and it's easily solved from there. Wonderful. So this is u substitution. I'm going to actually take a selection tool and move stuff over, because I want this to be visible on the screen to anyone who actually feels like they might need it. Oh! It's actually because I messed up the view on my document. Hold on. So if I go to clear. If I go to a, can I really not adjust my view? There we go. 1x. Wonderful. So yeah. That is u substitution. Then there's integration by parts, which relies directly on u substitution. And most things can be derived from these. There are neat tricks that you can always learn as you get further and further and further and further into calculus, right? But you'll find that math is something that tends to build on itself. So then we have integration by parts. So in integration by parts, we can basically say, let's say we have some integral that's difficult to solve, right? Like f prime of x equals x squared e to the x. This isn't difficult to solve, but just with our current tools, right, we have trouble. So how can we better solve this integral? Well, we can pick some value u that we want to differentiate, right? Let's say that's x squared, and then some value dv that we want to integrate. Well, we can then say, for the integral of u dv, that it's actually equal to uv minus the integral of v du. This is, you can derive this from the product rule, or a handful of other ways. In the lecture notes, I left a little link to a Stack Exchange, but I encourage you to sort of try to derive this yourself as a very difficult problem. So then you can say that du equals 2x dx, and v equals e to the x, right? So if we apply this rule twice, we get, let's just say it's from, okay, yeah. We basically get x squared e to the x dx equals x squared e to the x minus integral 2x e to the x dx. And then if we apply this rule again, which I do in the lecture notes, but for the sake of time, I'm just going to state what this is, right? So we get that this is two x e to the x minus 2e to the x, which gives us a total of x squared e to the x minus 2x e to the x plus 2e to the x, where we go from x0 to x1, right? 2 different points in x. Nice. Wonderful. And finally, we are on to trigonometric substitutions. So, for trigonometric substitutions, well, actually, no, we're on derivative identities, but I didn't really write enough for this because there's a lot to go over. But a lot of them are derived from the following identities, right? It's obvious from the unit circle. Well, not immediately obvious, but obvious with a little bit of thought. Right? Because these change proportionally to each other directly, and you can derive how they change relative to each other. And then you can see and that's really all you need, because you can use the power rule, or like the product rule, not the power rule, the chain rule, product rule, etc., for other trig identities. So this is really all you need to derive the other trig identities, and I would encourage you to try to do so for tangent and what have you. But finally, the last section I wanted to touch on is trigonometric substitution, right? Say, for instance, trig sub. Say, for instance, we have f of x equals square root of 1 minus x squared. Well, what can we do then? Well, we can say that we know that our x has to be between -1 and 1, if we want it to be on the plane of real numbers, at least. That's, again, another concept that I don't want to introduce here. Just know that for this to be valid in our case, this has to be true, right? We can say x equals sine of u. And then if we look at our rule up here, this one, right, we can say dx equals cosine of u du. So then when we solve an integral for when we solve an integral for f prime of x here, right? we can actually say that this is equal to cosine of u, or sorry, the integral. I apologize. The integral cosine of u 1 minus sine squared u du equals the integral of cosine squared u du. Now, in reality, this integral right here is a little bit of a pain to solve. There are very nice ways that you could solve it. There is a powers of sine and cosine trick, and there is also a hyperbolic sine and cosine trick that you can apply to solve these integrals quite nicely. But we don't need that typically in classical mechanics, and that is best saved for when we get to electrodynamics and other concepts in calculus that are more niche that you will likely need. So, I'd like to wrap things up here. We went through most of the basic rules of calculus that everything else can be derived from, and then some proofs for those. Though in reality, calculus is a series of units, and it's like a standard to make sure you're familiar with certain core competencies. So as you go further and further into any career or hobby involving the use of calculus, you sort of realize that you never stopped learning calculus. There are always cool tips and tricks for you to learn. And there are a lot of other tricks that I would like to teach that I haven't taught yet, like Feynman's trick, Gaussian integrals, the error function, differential equations, exact differential equations, and so on and so forth. And my hope is that you'll continue reading these either the lecture notes or continue watching the videos that I am going to be making, so that you can develop a greater understanding of calculus and an appreciation for calculus as you explore the subject more. Back when I was younger and I was doing my first explorations into more complex math, I had an amazing algebra teacher to help me build my intuition. But alongside that teacher, I found that Sal Khan and like Khan Academy, right? And I'm really going to emphasize this for calc. Khan cat Khan Academy was huge for me, right? It helped me sharpen my intuition for the subject, as well as my math skills. I was even able to learn most of calculus without ever having to touch a textbook, right? Stellar educator. So if you feel lost on any of the problems that I am going to be adding to the lecture notes, or if you feel lost on anything covered in this video or in the notes themselves, right? I would suggest maybe you take a look at Khan Academy as a resource, because it really helped me in my understanding of the subject, and it can give you a much better breakdown than a 50-minute to an hour lecture on Twitch could ever hope to do. Okay, and I actually ended on time for once. I thought I was going to need the extra 10 minutes I slotted in. If anyone else is here, questions, comments, maybe concerns? If not, I'm going to turn on the music and wrap things up here. Okay. Okay. Whew. So, I intend to do a lecture like this, ideally a little more prepared than I was this time. I was sort of freeballing it, because I wrote the last of it the other day, right? But hopefully I can sort of build up the subject for people and make it very approachable. And again, because I'm not like formally teaching a course or anything, I'm not gonna like offer you like homework that you have to do, right? Matter of fact, all of the textbooks that I give you, not like give you as in like you have the textbooks, that I recommend to you, contain excellent practice problems if you give them a try. Don't be scared to do those. I was always really scared to do those because I was like, man, I feel fucking stupid. You're supposed to feel a little silly and stupid when you first start out on things, right? I don't know. As regards my projects, a lot of these are on the back burner while I prepare myself for the process of trying to actually get into a grad school and show that I really can do what I want to do. So I might do a little series where I read papers. You know, if the papers are available for public access, of course, and I don't have to pay for them, because otherwise I couldn't read them on stream. And I might do a series where I talk about the things that I'm developing interests in. So, I don't know. I plan on doing this like 1 hour little lecture series every single week. It took me several hours of prep just to get a single hour out. So, you know, during exam season, it might slow down. But yeah, if you're either watching on YouTube or you're watching right now on Twitch, I really do want to thank you for stopping by. You know, it means a lot to me. I don't know. I've got a passion for sort of teaching people about the shit that I'm interested in. And I want everyone else to sort of develop a stronger appreciation for the subject that I've come to love as much as I do. Although, right now, it's a bit of a love-hate relationship. Yep. I'll update the notes and get rid of some typos. Because I noticed it was really bad. Like, one that was really bad. I'll actually fix that right now as I speak. Right. But, I don't... Remind me later. So earlier, in the video lecture... No, not video lecture. Lecture that I gave just a minute ago. Right? There was an issue in the notes. Again, most of you haven't seen the notes, but at least one of you watching probably has, if you're lurking, because I sent this out to a bunch of friends. It should actually be P to the N here, so I fixed that. And then there was a little bit of extra stuff I wanted to mention. Oh no, I added those in. Okay, wonderful. Yeah, and I'll try to get some exercises up for tonight, by either rewatching this and seeing what people had more trouble with, or by asking what people have more trouble with, so that you can really hone in your skills. But at the end of the day, my calculus practice problems are not going to be as good as the ones that have been honed for like ages and ages and ages and ages. Well, this has been an attempt at hosting a lecture on Twitch for calculus. Thank you for stopping by. I'll see you next week.